Okay, welcome to the first lesson of calculus flipped. So, today our goal is to calculate area between two curves in our Cartesian or Euclidean plane. This is the normal xy axis that we know and love. It's just the formal name for it. And our goal is to find area of shapes that we don't normally find area for. So, as you can see here, I have two functions, y equals 5x minus x squared and y equals x, plotted on the same graph. And I also have two integrations, definite integrals, set up here. Now for this purple area, which integral would I use? Of course, you know that integration is adding up an infinite number of rectangles between the function and the x-axis. And so this purple area would actually probably be the top integral here, from 0 to 4 of 5x minus x squared. And of course, that would get you between the parabola 5x minus x squared and the x-axis. And the bottom integration from 0 to 4 of x dx would get you the area between y equals x and the x-axis, like here. So that would actually be this red triangle here. Now if I wanted to find the area of the blue spot, it's pretty simple. Some of you might have already guessed what I need to do. If I take this purple integral and just subtract the red triangle worth of area, I should get just the blue area. So if I just take away that triangle, you see that I have something that's equal to the blue area over here. So, in short, to find the area of a region like this in between two curves, I find the area of the top, and I subtract the area of the bottom. And on the next slide, we're going to do just that. So now you can see that if I look at this rectangle, I'm finding the area between two curves there. This is going to be my delta x. That's the width between them. And I want that to go to 0. I want that norm or that partition to go to 0. Now the height of this rectangle is the height of the top function. I'll call that y sub 2. And this is going to be y sub 1. If I subtract y2 minus y1, I'll get that total height there. So my integration, if I set this up, I'm going from 0 to 4. That's the point of intersection right here. You can see that down there. So my bounds of integration would be 0 to 4. And I want the top function minus the bottom function. And I'll have a little dx because I have vertical rectangles. I have a delta x here. Now the top function is going to be this 5x minus x squared. And the bottom function, of course, is y minus x. And of course, I could do some algebra here to simplify 5x minus x. Those are like terms. I have 0 to 4, and it's going to be 4x minus x squared dx. We're going to use some general power rules and just integrate that thing. So we're going to have 4x squared over 2 minus x to the third over 3, and I'm going to evaluate that between the bounds of 0 and 4. Of course, 4 divided by 2 is just 2, so I'm going to write that as 2x squared. I'll begin by putting in the 4 by the fundamental theorem of calculus is what I'm using right now. And I want 4 cubed divided by 3 minus 0 over 2, right, minus 0 over 3. So that's really nice, and the second bound is 0. Now 4 squared is 16 times 2 is 32 minus 4 cubed, that's going to be 64 divided by 3. Alright, now in order to make this easier for myself, I'm going to make that out of 3. That's going to be 96 out of 3 minus 64 out of 3. You'll be left with 32 out of 3, or 10 and 2/3. In a calculator, you'd get 10 and 0.6 repeating, of course. But that's the area. I've found now how much space lies between the parabola and the line, not the parabola and the x-axis. Alright, now on this next slide, you have the same two graphs, y equals the square root of x and y equals x squared, and we're going to do it with both vertical rectangles and horizontal triangles. So, not triangles, rectangles, excuse me. So in this one, you see that the top minus the bottom is pretty easy to see. The top would be the square root of x, and the bottom that I'm going to subtract is x squared. That's the red line. I don't know why it's not working. One second here. Try it again. I'm using my new tablet here, so it's not quite as nice as I'd like to have it set up yet. X squared. And now I just need to integrate. What are the bounds of integration? Going from 0 to, looks like approximately 1 dx. And this is with respect to x. I'm going to pause real quick and just do the integration for you so I don't waste time. That after everything is said and done, using general power rules, I got the area is 1/3. Now over here it becomes a little bit more dicey because no longer is my rectangle Vertical, I have a horizontal rectangle. So now I'm not talking about delta x's anymore. My width is going to be delta y, and I want the delta y to go to 0. So now it becomes the question, what's this distance here? Well, obviously I'm on the x-axis and I'm no longer on the y-axis. So these functions should be in terms of x and not in terms of y. In other words, I need to solve for x. So to do that, x squared equals y. So therefore x equals the positive or negative square root of x. So we're just going to do the positive square root of y. The reason we don't have the negative square root of y is that would be this one. I know it's a little distorted, it doesn't look like the square root of y, but that's because my axes are labeled differently. So that's the first function down here. This one, if I have the square root of x, I'll do that over here maybe, equals y. If I square both sides, then I get x equals y squared. And which one's the top, the red or the blue? Well, you could see that the red now is the top. I'm looking at it kind of sideways, so I want the integration. What are the bounds? 0 to 1 again. And it's going to be, the top of it is the, the top one should be this guy, square root of y, minus, I don't know why it's not happening for me, minus, then this would be y squared. And you see that this is exactly the same integration that I had on the other one. It doesn't always work out like that, but this time it did because these functions are inverses. So when I switch the x and the y, I should get the same thing. And so my area, of course, would work out the same. Area equals 1/3. Alright, so what did we learn? If the rectangles are horizontal, my function needs to be solved for x. And you need to decide which of those functions is farther to the right or on top. If I were to turn the screen 90 degrees counterclockwise, this one would be farther to the top. Basically be x2 minus x1. Oops, too far. So on this graph, would we be using vertical or horizontal rectangles? In other words, will it be solve for x or solve for y? Kind of gave it away, I suppose, by giving the function rules. We're going to be using horizontal rectangles. So what are the bounds of integration? Well, integrating looks like from this intersection, where they meet, at -2, and we're integrating to this intersection, which looks like 4. And so which one is farther to the right, the blue or the red? In other words, if I drew a rectangle here, what's going to be the top of the rectangle relative to the y-axis? Well, the top is going to be the blue function. So we're going to take the blue function, which is y plus 1, again, solve for x, that's why it's in terms of y, minus the bottom function, which is this red parabola, which happens to be 1/2 y squared minus 3. Now I'm going to integrate that all with respect to y, dy. Alright, I'm going to pause again and just do the integration just to save time. You can see here now that I have it all set up. And I have -64 plus 48 plus 96 divided by 6, and so that's going to be -16. I'm sorry, 80. That's -16 plus 96 is 80 by 6 minus, and then this one is going to be 8 plus 12 is 20 minus 48 is -28. 6 minus the negative, you'll be adding, so it would be 108 over 6, which ends up being, I believe, 18. Double check here real quick, I just want to make sure I didn't make a mistake. There once. 6 times 8 is 48. There you go. 18. So the area that I've encompassed in the gold there is 18. Now, if you didn't follow my steps, I'm just going to go through them one more time. I subtracted the blue minus the red. That leaves me with a -1/2 y squared. Y minus no other y's is positive y. 1 minus a -3 is positive 4. I integrate with the general power rule. I substitute in my bounds of integration using the fundamental theorem of calculus, and I find the area of the region. Now here's another tricky one that's using trigonometric functions. Will I use vertical or horizontal rectangles in this one? Well, if you use horizontal rectangles and have it in terms of y, that would be rough because then you'd have to kind of do two different integration problems. So we're going to use vertical rectangles. And so you're going to have the functions switch places. You can see on the left side cosines on top and the right side sines on top. There's this point in the middle where they meet. So I'm actually set up two different integrals. At the first intersection at pi over 4, I go 0 to pi over 4, and I begin with cosine on top. So it's going to be cosine of x. I guess it should really be theta if we're talking about angles here, but I'm not going to be super picky, so I'm going to subtract cosine of x minus sine of x. I'm going to integrate that with respect to the independent variable x, plus, and then I have to add that. What I just did there is find this region, right? And now I have to integrate from pi to 4 to pi over 2, but now they switch places. Sine is on top, so I have to subtract sine of x minus cosine of x, and that's the red function. 1 second here, let me get that red. And that's going to be in with respect to x also. Saving time, I'm going to integrate for you. See, I'm sure that if you pause and went through this yourself, you'd see that you'd get the same answers I did. I'm just using general rules of integration here, and so if you follow the instructions and go through, you should get 2 square roots of 2 minus 2 equals 0.828. Now it's worth noting here that these two regions are equal, and you could see that kind of just intuitively, but you could just, if you find out by doing one of them, you'll get exactly half of what I got my answer to be. So if they're symmetric like these two regions are, if they're both equal, you could just do the integration of one of these, like this one I'm cross-hatching, and just multiply by 2. Because that area is half of that, or 0.414. Now, I don't think it's really necessary for me to go through this one. Just for brevity of the video, you could see that I'm going to set up 2 different integrals, but I'm not going to actually integrate it. So you can integrate these, and of course, on the left side, they intersect where the red's on top. Well, the red function is 2x cubed. I should use the same color. There you go, 2x cubed minus x squared minus 5x. Now you're going to have to subtract the blue function, which ends up being negative x squared. And note that I have to subtract the entire thing here. And that's your first integral. Then you'd have to add, and what I should add the bounds of integration. I'm going from, looks like, -2 to 0 on that one. The other one I start where I left off at 0, and I go to +2, but now the blue one's on top. So you can see here that I have negative x squared plus 3x minus the red function. Don't forget to subtract the entire thing, so you're going to distribute that negative sign to all the terms. And that's going to be with respect to x, because I'm doing vertical rectangles, so you can see that. That's going to make it easier. It's a really bad rectangle. And so I'm not going to go through this integration. You could use that if you want more practice or if you just to get the hang of it, but you can see that our goal was to calculate the area between 2 curves, and I think that we got that done. So check my little box here. Here's your homework assignment. That's what we're going to be working on in class. If you've never had a flipped classroom, that means that during class we're going to work through these exercises and do a couple more things just to make sure you understand the concept. Thanks for watching.